Hello everyone, welcome back to machine learning, and today we'll discuss about polynomial curve fitting. Through this discussion, you'll learn about data generation and sampling process, formulating a regression problem, how to do polynomial curve fitting, and what are hyperparameters, what is overfitting, and how to solve it. Let's start our discussion by assuming that we have access to a sine function of the form sine 2 pi x and a Gaussian noise generation process. What is Gaussian noise? We'll talk in detail later, but for now think of it as a method to corrupt a real world signal. For example, an audio signal recorded through a microphone might have some background noise. So formally, we can write a data generation process as t equals to sine 2 pi x plus eta, where x is the input, eta is the noise, and t is the output, while sine is the underlying generation function. Now let's say that you have access to only 10 points that are obtained using this function. In vector form, the input for 10 points can be written as x equals to x1, x2, x3 to xn. And similarly, the output can be written as a vector t, which is t1, t2, t3 up to tn, and n is equals to 10 in our case. The figure on your screen represents the original function in green. So this is the original sine 2 pi x function without any noise. And the blue bubbles represents the noisy data points, and we have only 10 of these. You should note that all the points are not exactly on the curve. This is because of the noise. So for example, let's say you have x1 which equals to 0. The corresponding value of t, that is t1, for this signal should be 0 if it is a pure sine function. But since it is a corrupted sine signal and the corruption is due to the noise, so we have some variance of t1 from 0. So the blue bubble is not exactly at 0 for x1 equals to 0. So this is due to noise. So in practice, what we have access to is only these blue points, the noisy data points. We do not have access to the underlying green function or the original signal generating function. Now the problem boils down to, given a set of points, we have to estimate the underlying function. This is known as a regression problem where you are given some noisy data points as observations and you're asked to estimate a real valued output for a new input. Regression problems, in contrast to classification problems, give real valued outputs instead of categorical ones. For example, in the last session, we discussed cat versus dog classification problem. So instead of giving categorical outputs, the regression problems gives real valued outputs for given inputs. The known input-output pairs become your training set, and the new inputs for which you have to estimate the output becomes your test set. A simple approach to solve this regression problem is to fit a polynomial model on the given training data points. By fitting, I mean you assume that the relationship between the input and the output is of polynomial nature as given by this equation. So here your x is the input and y is your estimated output. Note that t was your original output and here y is the estimated output because you do not have access to the original sine function, but you assume that the given data points, they can be approximated by using a polynomial function. So that's why this y is your estimated output. So polynomial function can be written in a simple way as a sum and product of the coefficients and the inputs raised to the power their polynomial order. So here the polynomial goes from j equals to 0 to m, where m is the order of the polynomial and training is the process of estimating the model parameters. Note that the coefficients or weights are parameters. W1, W2, these are the coefficients and these are known as parameters of the model, and the order of the polynomial is known as hyperparameter. This is because order of the polynomial is not directly associated with the inputs. Only the coefficients are multiplied with the uh, inputs that are raised to some power. So often a small subset of training data known as validation set is set aside to estimate these hyperparameters. But let's just proceed with training and testing our polynomial model for a while. We'll talk about validation set a little bit later. The values of the coefficients can be estimated by minimizing the error between the predicted outputs and the correct outputs. A common error function used for this purpose is sum of square errors. Formally, it can be written as follows. So here you have the original output Tn. You take the difference between the estimated output and the original output. You square this for each point, and then you add the error of all the points and multiply it by half. Uh, Visually, this error function is represented as in this figure. So you have a polynomial curve which is shown in red here. You have the original data point Tn, and for nth output you have the output estimated output y at xn as a function of weights of the polynomial. You compute the error between Tn and the estimated output. You square this error, and then you add the squared error for each term, each data point, and multiply it by half to get the error function. You should notice that this error function is a function of w. So only unknowns in this term in this function is w, because xn is known, tn is known, so y is dependent only on w. To, to minimize this error, we should take the gradient of this error function with respect to the coefficients, since coefficients are unknown. And for this particular problem, it will give a unique solution. Why it will give a unique solution? Because you have n set of equations to solve this gradient, to solve the gradient of this error function. So since you have n linear equations to solve for, you can easily get a unique solution, and you can verify that by taking the gradient of this function. The half before the quadratic term is to cancel out with the 2 that comes down after differentiation during the gradient minimization procedure, and that's the precisely for the precisely the reason behind the existence of this half. Now we are left with the question of selecting m. You know that we can estimate w's by taking gradient of this error function, but how to select m? Let's move on to that discussion. Since we are not discussing about validation set based model selection, we'll estimate the hyperparameter m empirically. This means that we'll try out different values of m and see which one gives us the best fit. Here is a crucial point. What should be the measure of the best fit? Should it be error on the training data or an independent test data? Let us try to understand this by first starting out with m equals to 0. When m is equals to 0, you get a constant function which is w0. So this is shown by a red line on your screen. So as you can see, this red line for m equals to 0 is not a good approximation of the underlying uh, original sine function, which is shown in green. Now you can imagine that this will lead to large errors on the training set. So this is not a good approximation of even for the training set. So it cannot be a good approximation for the test set. So this is clear. Let's move on to the first order polynomial. If we plug in m equals to 1, then we'll get a first order polynomial written as w0 plus w1x. So you can say w0 is your bias and w1 is your slope of the estimated signal or approximation. So you see the red curve is still not a good approximation of your underlying original signal generation function. So this will also give some errors on the training data, and you can imagine that the error on the training data itself will be very high. So it is not a good approximation for the training data points as well. Let's move on to m equals to 3, which gives you this function, which is w0 plus w1x plus w2x squared plus w3x cubed. So now you can see your red curve is quite a good approximation of the underlying green curve. So your red is the approximation or the regression function, which is polynomial in this case, polynomial of third order in this case, and your green one is the underlying data generation process. So even though there are some errors on the training data by using the red curve, but these errors will be less than the errors computed by linear curve and or the constant function. So by this logic, if we keep on increasing the order of the polynomial, we should get better approximations. So let's say we fix the order m equals to m equals to 9. So as you can see on the screen, this is a very oscillating function. So you can see when we plug in m equals to 9, our red curve is highly oscillating, but it passes exactly through each of the data points, each of the training data points. So if you see, if you compare this m equals to 9 with m equals to 3 curve, so you see m equal to 3 curve passes through some of the data points, but not exactly through all of this. It in some way incurs some error on the training set. But when you go for m equals to 9, the error on the training set becomes exactly equals to 0. So our red curve is perfect approximation for the training data points, is a perfect fit for the training data set, as it doesn't give any error on the training points. But as you can imagine, this is not a good approximation of the underlying sign function. So whenever you plug in a new data point, let's say here, so you have a new test point x test here, your output will be this, not exactly this or near this. So your error on the test points will be very high. Although you minimize the error on the training points, so the error on the test points will be very high. So this is popularly known as overfitting. So your model overfits to the training data points. So it passes through every training data, but whenever you plug in a new test point, it gives erroneous results. So this is called overfitting. So let's start our discussion on overfitting in more detail. For this, we have to see the generalization performance of these two models. By two models, I mean m equals to 3 versus m equals to 9 and so on. By that, I mean we should estimate the outputs and compute errors for an independent set of inputs. To do this, we'll resample, let's say, 100 more points from the original noisy sign function and compute the target value for each of these new points to compute the errors between the original and polynomial predicted values. So in simple words, what it means, so you have new 100 x points and input points, you compute the corresponding true output from your signal generation function, and you also plug in these input points into your polynomial approximation to get the predicted outputs. Then you compute the error between the original 100 outputs and the predicted 100 outputs, and you compare these errors by changing m. Okay, so for convenience, we'll compute root mean square error, which is 2 times the original error divided by n, and we take its square root. So n accounts for the varying number of points. So you might have 10, 100 or whatever test points, and 2 is to cancel out that half, and then square root is to force these error values to lie between 0 and 1, which is the same range for the values of the outputs, to have a fair comparison. The plot of this error relative to the polynomial order is shown in this figure. As you can see, the training error reduces to 0 for m equals to 9, but the test error is very high. So when m equals to 9, your training error is is exactly 0, but your test error is very high. This is because the ninth order polynomial exactly fits the training data but doesn't generalize well to a new test sample. This problem is known as overfitting. On the other hand, if we select m between 3 to 8, our model gives good performance on both training and test data. So we can confidently choose m equals to 3 which is the least complex, best performing model. So here is the way to select the models. One way to select the models. You should select the models which gives you good performance on the training data as well as an equivalently good performance on the test data. And between the models of different complexity that satisfy this criteria, you should choose the model which has least complexity. So this is the way to select the model. Now let's move on to a more deeper understanding of overfitting, that why overfitting happens or what leads to overfitting. For this, we have to examine the weights or coefficient values of the polynomial function. As shown on your screen, we can see that as we increase the order of the polynomial, the coefficient values become very large. So you can see with m equals to 1, so you have some coefficient values, but as you move on to m equals to 9, the coefficient values become surprisingly very large. So let's take out the sign out of this picture. If we compare the absolute values, so these are very large coefficient values when we have a higher order polynomial. This is because the polynomial function of order 9 tries to fit every training data point exactly, and in doing so it oscillates a lot in between the points. In perspective, the training points themselves are noisy and the function gets tuned to this noise during overfitting. So in the starting, we mentioned that our data points are noisy, and when we have a higher order polynomial, the polynomial tries to fit every training data point exactly, and in doing so, it gets fine-tuned to the data noise. That's why it oscillates a lot between these two, between the between the training data points. So, how to overcome overfitting? So, how to avoid overfitting? So there are two approaches to do this. One is to increase the number of training points, and you can see from this example that as you move on from 10 data points to n equals to 15 data points from the ninth order polynomial, so your error gets reduced. And let's say we increase the number of training data points to 100, and then your red curve almost overlaps with the underlying green curve. So one way to avoid overfitting is to increase the number of samples in the training data. So let's say we do not have enough training samples. How we will avoid overfitting in that case? So there is an alternative way to do this, and that is known as regularization. So we'll talk about regularization now. So regularization involves adding a penalty term to the error function to discourage the coefficients from taking larger values. A common form of penalty is L2 regularization, which minimizes the inner product. So this is L2 regularization, which is written in this form. So this is the inner product of the weights or the length of the weight vector. So what it means is you simply square each coefficient and add those squared coefficient values to compute the L2 norm. So you add this term in the error function and then you minimize this error function by taking the gradient. Here you give the relative weight to the L2 penalty to give importance to either the data reconstruction term or the regularization term. But you have to choose such a lambda that gives you good function approximation as well as keeps your coefficient values to a smaller range. So let me show you some coefficient values for different for varying values of lambda. So when your lambda is very high, so you have very small coefficient values. This is one extreme. And when your lambda is almost zero or exactly zero, so you have very coefficient values. So here there is no regularization. Here there is extreme regularization. So you have to choose something in between that gives you good error reconstruction value or good performance on the training data, as well as keeps the coefficient values low. Why the lambda values are in log scale? This is just to keep things simple, because as you can see here, your lambda is very small. Lambda is equal to e to the power minus 18. So if to write this value, it is very tedious. So to keep it simple, so we use logarithmic scale. And here your lambda is equal to 0, so your log lambda is minus infinity, and here your lambda is equals to 1, so your log lambda is equals to 0. So it's a quite big scale. So you can choose lambda anywhere between 0 to 1, and there are infinite values in between. So in order to compare those values, so we use this log scale. But the point is, you should not choose your lambda to be very small or very large, but it should be some intermediate value that gives you good training performance while keeping your coefficients small. That is avoiding overfitting. Now, there are various types of regularization penalties that have been proposed in the machine learning literature. We have already discussed L2 penalty, which is the sum of the square of the individual coefficient values. And then there is L1 penalty, which is also known as L1 norm, which is the absolute values of the weight coefficients summed together. So instead of squaring and adding the coefficients, you take the absolute values of the weight or coefficients and you add them together to form L1 penalty. L2 penalized regression is popularly known as ridge regression. L1 penalized regression is popularly known as lasso. So lasso means least absolute shrinkage and selection operator. So your L2 is regression and L1 is lasso. And then there is elastic net model, which combines L1 penalty and L2 penalty into a single model. So there are three types of regression models which we discussed: L2 regularized regression, L1 regularized regression, and elastic nets. So with this discussion, we are only left with a small discussion on hyperparameter selection. Now we have two hyperparameters, m and lambda, in our model. So your order of the polynomial and the weight of the regularization term. So in elastic net, you have two weights, lambda 1 and lambda 2. You can combine these lambda 1 and lambda 2 by saying, let's say we weight this by 1 minus alpha and we weight this by alpha. So your regularization hyperparameters become alpha. In nutshell, we have two hyperparameters to select. One is m and lambda. Usually we partition the training data into two bins, one for training the model and another for the validation of the model to select the hyperparameters. Usually 80% of the data forms the training set and rest 20% of the samples are used for validation. It should be noted, however, that the test data is completely untouched during training and hyperparameter tuning. Okay, you train your model on the training samples. You select the hyperparameters using your validation set, but you feed the test data only to evaluate the model performance, not during training or model selection, hyperparameter selection. And it is the test set that finally tells us about the generalization performance of the model. So the most important criteria in model selection should be the performance on the test set. Although your model should fit the training data with minimum possible error, but the error on the test set should be the guiding factor for model selection. So with this, we close our discussion on polynomial curve fitting or polynomial regression. In the next video, you will learn how to implement polynomial curve fitting in Python. Thereafter, we'll start our discussion on the basics of probability that are essential to understand any sophisticated machine learning algorithm. So stay tuned to our machine learning channel. Hit subscribe, like, and share the video among your friends, and click the bell icon to receive updates whenever we upload a new video. Thank you.